When we gaze at the night sky, what we see feels boundless. Stars speckle the darkness like grains of sand scattered across an infinite beach. Yet what appears infinite to our eyes is, in truth, limited by one fundamental rule of nature. Light has a finite speed. It does not cross space instantaneously. It must journey step by step, taking years to reach us. When we look outward, we are also looking backward in time. A star seen tonight may have cast its light millions of years ago. The universe offers us not a direct picture of the present, but a record of ancient events still racing across the void. This limitation defines what cosmologists call the observable universe. It is a sphere centered on us, stretching about 46 billion light-years in every direction. Anything beyond that limit has not had time to send its light or any signal to Earth since the moment the cosmos was born. Imagine standing on a ship in the middle of a vast ocean. No matter how sharp your eyes, your vision halts at the horizon where the sea meets the sky. You know the ocean continues beyond that circle, but you cannot see it. The observable universe is our cosmic horizon, an edge drawn not by walls of matter, but by the simple fact that light has not yet arrived from farther regions. To understand why the limit is so vast yet still finite, consider how light and expansion intertwine. The universe has existed for about 13.8 billion years. At first glance, one might expect the observable boundary to be 13.8 billion light-years away. But space itself has been stretching throughout cosmic history. Light set out when the cosmos was young, crossing expanding terrain. The journey is elongated, the distance is magnified. That is why the present observable radius is closer to 46 billion light-years. The boundary is not a snapshot of distance alone, but the result of light racing through a dynamic, swelling space. The very phrase observable universe carries a humbling lesson. It does not mean that the cosmos ends at that distance. It does not mean that galaxies vanish into nothingness beyond. Just as the sailor trusts the ocean continues past the horizon, astronomers understand that reality extends well beyond our visible boundary. What we call the observable universe is simply the region we can in principle detect. Everything else lies hidden for now. This distinction is crucial because without it, one might imagine that the cosmos has a literal edge, a wall enclosing existence. In fact, there is no such border. There is only a limit to our reach. Picture again the ship and the horizon. If you were to travel across the sea, your horizon would shift with you. In the same way, every observer in the cosmos has their own observable sphere. A distant galaxy hosts astronomers who see their own sky, with a horizon just as far as ours but centered on them. What is beyond our horizon is not beyond theirs. In this way, the universe overlaps itself, with billions of cosmic horizons interwoven, each revealing a different but consistent piece of the greater whole. The horizon is personal, yet the cosmos itself is collective. The cosmic horizon is also not fixed. As time moves forward, light from ever more distant places has time to arrive. Our sphere of visibility grows. We now see galaxies whose light has been traveling for over 13 billion years, nearly to the dawn of cosmic history. In billions of years to come, astronomers will see even farther. Yet there is a counteracting truth. While we can see more with time, the expansion of space pulls galaxies away faster than light can bridge the gap. Eventually, many galaxies visible today will slip permanently beyond reach, their light stretched into invisibility by the growing void. The horizon grows, but at the same time, the contents within it shrink. The future will hold a sky with fewer galaxies, not more. To contemplate the cosmic horizon is to recognize our fragile position in time as well as space. We live in an era when distant galaxies are still visible, when the faint echo of the Big Bang, the cosmic microwave background, still bathes us in ancient light. Far in the future, that evidence will fade. Observers then will have less access to the truth of cosmic origins. The horizon teaches us not only about distance, but about the fleeting opportunity of discovery. We are fortunate to live at a moment when the cosmos reveals its vastness. And so, the horizon is not a wall, but a mirror of our limits. It marks how far we have come in understanding and how much remains hidden. Beyond it, galaxies exist that we will never touch. Beyond it, perhaps other wonders too great for imagination. The horizon whispers both possibility and humility. It tells us that the universe is larger than our sight, and that our quest to know must embrace what we cannot yet see. As the sailor senses the unseen sea beyond the circle of vision, we too sense the continuation of reality past our horizon. The observable universe is a doorway, and beyond that doorway lies the infinite unknown. We stand on the threshold of that unknown, aware of its existence but unable to cross. We can measure, calculate, predict, and dream, but the light from those regions has not yet reached us, and some of it never will. Still, the recognition that reality stretches beyond our horizon is perhaps more profound than seeing it directly. It means that we inhabit a cosmos larger than comprehension, a stage vast enough to dwarf every human story. The horizon is not the end of the universe, it is the beginning of wonder. And so the story continues. Beyond this horizon, reality unfolds in ways both knowable and forever hidden. What lies outside our sphere of light is as real as what lies within. As we turn from the horizon itself to the nature of the universe's expansion, we step into the deeper currents that shape not only what we see, but why we cannot see it all. The horizon points us forward, toward the great mystery of the expanding cosmos. The cosmic horizon is not a single idea to grasp in one glance, but a perspective we must circle around slowly, like walking along the railing of that ship and realizing the horizon surrounds us in every direction. Each step deepens the sense that this limit is not merely a trick of vision, but a profound statement about the structure of the universe. We are bound not by walls of matter, but by the rules of relativity itself, rules that insist information cannot travel faster than light. To understand why this is so central, imagine two events separated by great distance. If a burst of light leaves one and tries to reach the other, it cannot outrun the fabric of space-time itself. The finite speed of light means that when we receive the glow of a distant galaxy, we are glimpsing its ancient past. The farther the galaxy, the deeper into history we peer. Look far enough, and we approach the very beginning, a faint glow when matter first cooled enough to allow light to travel freely. That ancient radiance, stretched into microwaves by billions of years of expansion, fills the sky as the cosmic background. It is the ultimate wall of sight, the farthest ancient light that physics allows us to detect. Yet even this wall is only an apparent one. The galaxies beyond that early light still exist, forming, colliding, and evolving beyond our reach. They are not hidden because they are unreal. They are hidden because space-time conspires against our view. If the cosmos were static, if distances remained fixed, then the observable universe would slowly reveal itself entirely. Light would eventually reach us from every corner. But because space itself expands, carrying galaxies away faster and faster, there will always remain places that never send us their light. This is why the horizon is not just a temporary veil, but a permanent frontier. Consider the strangeness of this. A galaxy may release a photon of light in our direction, yet the fabric of space between us stretches so swiftly that the photon never closes the gap. It is like a swimmer trying to reach shore while the tide pulls them backward faster than they can swim. The photon tries eternally, but the distance grows faster than progress can be made. The result is that entire realms of the cosmos are sealed away from us forever, not by barriers of matter, but by the relentless acceleration of expansion. This truth reshapes how we imagine the universe. Instead of being a single shared stage where all events are in principle connected, it is more like an archipelago of regions, each with its own accessible history, separated by oceans of unattainable distance. Our observable universe is one such island. Others exist beyond, unreachable. And in their own skies, the story of the cosmos looks both familiar and strange. Familiar because the laws of physics are the same. Strange because the specific galaxies and clusters they can see differ from ours. Reality is vast, yet our view is always provincial. If we could somehow pause expansion and wait, the horizon would indeed recede, letting more and more of the cosmos fall into view. But expansion is not slowing, it is accelerating, driven by the mysterious influence we call dark energy. The farther galaxies are, the faster they are swept away. That acceleration ensures that even as time passes, the horizon holds its grip, and many galaxies vanish beyond it. This sets a haunting fate for the night sky. Today, through the most powerful telescopes, we can see galaxies billions of light years away. But in the far future, these distant islands of light will fade and disappear, leaving only the few galaxies gravitationally bound to our own. Astronomers billions of years from now may live beneath a sky emptied of its evidence, with no way to infer the true size of the cosmos. It is sobering to think that the richness of the cosmic sky is temporary, a passing window in history. We live in an era of extraordinary visibility. This moment is one when the cosmos reveals itself in both depth and breadth. We see back to near the beginning and outward across unimaginable distances. The horizon allows us to measure not only what is there, but how it changes with time. In this way, the horizon is a teacher, instructing us not only about physics, but about the fleeting nature of knowledge itself. And yet, while humbling, the horizon is not despair. It does not tell us the cosmos is small, it tells us it is larger than imagination. The horizon marks the edge of what we can know directly, but not the edge of what is. It is the reminder that beyond our reach, reality continues, just as the sailor knows the sea goes on. The observable universe is our lighthouse, illuminating a circle of reality. But the darkness beyond is not nothingness. It is simply the unlit expanse awaiting its own story. As we turn toward the next stage of understanding, we find that this horizon is not static, but dynamic, shaped by the very expansion of the universe itself. To see why, we must step into the story of cosmic motion, the discovery that galaxies are not merely drifting, but are carried by the stretching of space. In this expansion lies the reason the horizon exists, and the key to understanding the larger tale of what may lie beyond it. The horizon is a boundary defined not by our will, but by the laws of the cosmos. It is a circle of possibility, enclosing everything we can in principle observe, and reminding us at the same time of all that lies beyond. When we consider its meaning, we find ourselves at the intersection of physics and philosophy. For the scientist, the horizon is a measurable feature, determined by the age of the universe, the speed of light, and the rate of expansion. For the dreamer, it is a metaphor for the limits of human knowledge, a reminder that there will always be more beyond our grasp. Think of a child staring at the sea for the first time. The line where the water meets the sky feels like the edge of the world. The child may wonder if ships that sail across it fall into nothingness. Only later comes the realization that the horizon is not the end, but the beginning of a wider ocean. Humanity stands in the same position with respect to the cosmos. We see the curve of our cosmic horizon and wonder what lies past it. In truth, the cosmos continues, perhaps endlessly. Our horizon is not the end of the world, it is the beginning of a larger reality. In modern cosmology, this truth is made precise through observation. We measure the faint afterglow of the Big Bang, we track the redshift of galaxies, we calculate how space expands. These are not guesses, but carefully tested facts. They allow us to define the horizon with remarkable accuracy. And yet, as precise as these measurements are, they also deepen the mystery. We can state the radius of the observable universe as about 46 billion light-years, but we cannot state the size of the entire cosmos. It may be hundreds of times larger or infinite. Our instruments give us a number, but they also reveal the vast unknown. This unknown is not empty. Beyond the horizon, galaxies form and stars burn. Supernovae explode, planets orbit, perhaps even life stirs. None of it is available to our sight, but it exists nonetheless. The horizon does not confine reality, it only confines what we can know. This distinction matters because it shifts our perspective. We do not live at the center of the universe, nor do we live at its edge. We live within one bubble of visibility in a sea of reality that stretches beyond imagination. Our place is both central to ourselves and insignificant to the whole. The most striking fact about the horizon is how it makes the universe a time machine. When we look outward, we are looking backward. We see galaxies not as they are today, but as they were billions of years ago. The edge of the observable universe is not the present state of distant realms, but their ancient history. The galaxies we glimpse near the horizon may no longer even exist. They may have merged, transformed, or faded. What we observe is a fossil record written in light. In this way, the horizon is not only spatial, but temporal. It tells us where we are in time as much as in space. This intertwining of time and distance raises questions that stretch beyond science into philosophy. If what we see is always the past, then the present universe beyond our sight is forever hidden. We must live with the fact that we cannot know reality in its entirety. Our picture is always partial, always delayed, and yet, this limitation is not a flaw of the cosmos. It is the natural outcome of living in a universe governed by relativity. To ask for more is to ask for a universe that is not our own. What then should we make of this? Perhaps the horizon is a lesson in humility. It tells us that our knowledge, no matter how vast, is always finite. It tells us that there will always be mysteries beyond our reach. At the same time, it invites us to wonder. The very existence of an unseen cosmos sparks imagination, inspiring us to ask questions, to explore not only with telescopes, but with thought. The horizon becomes a frontier, not a prison. It challenges us to expand the boundaries of theory, to imagine what cannot be seen, and to search for indirect clues that whisper of the greater whole. In this way, the horizon serves as a bridge. On one side lies the realm of measurement, the numbers and data of science. On the other side lies the realm of speculation, of what might be true beyond sight. The two are not enemies, but partners. The horizon defines where science stops and imagination begins. Without one, the other would be incomplete. Science gives us a circle of truth. Imagination carries us beyond it. As we close this chapter, we return to the image of the sailor and the sea. The horizon surrounds us, inviting both caution and curiosity. It reminds us of the vastness we cannot see, but also of the wonder that lies in seeking to understand it. The observable universe is our current map, drawn with care and precision. But every map ends in blank space, in regions yet unexplored. Beyond our horizon lies that blank space. And in the next stage of our journey, we will turn from the limits of sight to the story of motion itself, to the great expansion of the universe that carries galaxies outward and sets the horizon in place. The sea continues, and so does our voyage. When astronomers at the dawn of the 20th century looked at the spiral nebulae through their telescopes, they could not yet decide whether these objects were distant galaxies or mere clusters of stars within our own. The debate stretched across decades until greater instruments and sharper eyes revealed the truth. These spirals were island universes of their own, billions of stars bound together, scattered across a cosmos far larger than the Milky Way. But the true revolution came when Edwin Hubble and his colleagues began to measure not only the distances to these galaxies, but also how their light shifted toward the red end of the spectrum. That subtle reddening carried an extraordinary message. It told us that the galaxies were not standing still, they were receding. At first, this discovery was almost too astonishing to believe. The natural assumption had long been that the cosmos was static, eternal, and unchanging on the largest scales. Stars might burn and die, galaxies might form and collide, but the universe as a whole was thought to be stable. Hubble's observations shattered that view. The farther a galaxy was, the faster it seemed to be moving away. The relation was so clear, so linear, that it could not be coincidence. Something fundamental was happening. The universe itself was expanding. It is important to understand what this expansion means. The galaxies are not rushing outward into empty space like fragments from an explosion. Instead, space itself is stretching. Imagine a rubber sheet with dots drawn upon it. If the sheet is pulled taut in all directions, the dots move away from one another, not because they themselves are moving across the surface, but because the surface itself is enlarging. In the same way, galaxies are carried apart not by their own motion, but by the growth of the cosmic fabric. This is why there is no true center of expansion. Every galaxy sees others receding, just as every point on the stretching sheet sees all other points moving away. The discovery of cosmic expansion changed not only astronomy, but philosophy. It implied that the universe had a beginning, a moment when the fabric of space was far smaller, hotter, and denser than today. This realization gave birth to the Big Bang theory, which remains the foundation of modern cosmology. The expanding universe is not just a detail of physics, it is the grand stage upon which cosmic history unfolds. Stars form, galaxies cluster, and life emerges, all within a cosmos that is forever stretching outward. Yet expansion also carries a profound consequence for our understanding of the observable universe. Because galaxies are carried away by the growth of space itself, there comes a point where their recession exceeds the speed of light. This does not violate relativity, because no galaxy is moving through space faster than light. Rather, the space between us and them is swelling so quickly that even light cannot bridge it. Such galaxies cross beyond our horizon, becoming forever invisible. We know they exist, but we will never see them again. This realization changes how we imagine the cosmos. We often think of the universe as a great hall in which all events could in principle be witnessed if only we were patient enough. Expansion denies this. There are galaxies that no amount of waiting will ever bring into view. There are events whose light sets out in our direction, but never arrives. In this way, the expanding universe creates not only the cosmic horizon, but also a separation of realms, dividing the visible from the forever hidden. It also means that the sky of the future will not resemble the sky of today. As space expands, the light from many galaxies grows fainter and redder, stretched into wavelengths that slip beyond detection. Slowly, they fade into darkness. What remains are the galaxies close enough to resist expansion through their own gravity. Our local group, the small family of galaxies, including the Milky Way and Andromeda, will endure. But the countless other galaxies now seen will eventually vanish from sight. The night sky will become emptier, the cosmic tapestry unraveling thread by thread. For those who live billions of years from now, this will obscure the true nature of the universe. They may look up and see only a handful of galaxies, never knowing that once the sky blazed with hundreds of billions of them. They may have no evidence of the Big Bang, no cosmic background radiation, no expanding web of galaxies to measure. For them, the universe may seem static once again. This fate is a reminder of how privileged we are to live in an era when the cosmos reveals its secrets. The expanding universe also hints at mysteries deeper than distance. What drives the acceleration of expansion? Observations show that galaxies are not only receding, but receding faster and faster. Something, a form of energy embedded in space itself, pushes outward with relentless force. We call it dark energy, though the name is little more than a placeholder for ignorance. Its nature remains unknown, but its effect is clear. It ensures that the horizon will always exist, and that more and more of the cosmos will slip beyond it with time. The expansion of space is therefore not only a scientific fact, but a philosophical challenge. It tells us that the universe is dynamic, that change is the rule, even on the largest scales. It tells us that knowledge is temporary, that what we see today is a fleeting glimpse. It tells us that we live within a cosmos that grows beyond us, stretching away faster than comprehension. And it invites us to ask what lies beyond the horizon that expansion forever hides. From the vantage of Earth, we are fortunate witnesses to this grand unfolding. Our telescopes capture the faint light of galaxies at the edge of visibility. Our instruments detect the subtle glow of the background radiation. Our theories knit these observations into a story of origin and growth. The expanding universe is our greatest revelation, the key that unlocks the past and hints at the future. It is the canvas upon which all cosmic events are painted. But this canvas is larger than what we can see. The expansion suggests that beyond our horizon, the cosmos stretches on, perhaps endlessly. It hints that what is visible is only a fragment of a greater whole. The horizon, once again, is not an end, but a beginning. To follow the thread of expansion is to be led into speculation, into realms where the universe is far vaster than observation alone can show. And so our journey continues, from the known into the unknown, from measurement into imagination. The expanding universe opens the door to the next chapter of our story, the tale of cosmic inflation. For while expansion continues today at a measured pace, the early universe underwent a burst of growth so rapid and so violent that it defies ordinary description. This inflation may explain why the cosmos looks the way it does, and why our observable universe is only a small bubble in something far greater. Expansion has shown us that the universe grows. Inflation will show us how that growth began. The vision of an expanding universe forces us to reimagine the very stage on which existence unfolds. For centuries, philosophers pictured space as a static backdrop, a vast emptiness in which stars and planets drift like actors across a fixed stage. The discovery that space itself stretches contradicts this deeply rooted image. The backdrop is not fixed. It swells and changes. The curtain itself moves. Every galaxy is carried apart, not by its own momentum, but by the expansion of the arena in which it resides. To appreciate how strange this is, imagine dots painted on the surface of a balloon. As the balloon inflates, each dot moves farther from every other. From the perspective of any given dot, it seems as though the others are fleeing. But in truth, no dot is in motion of its own. It is the balloon that changes, carrying the dots with it. The same is true of galaxies. When we observe their light shifted toward the red, we are not witnessing them speed away through static emptiness. We are witnessing the stretching of space itself. This distinction matters because it explains why there is no center to the universe. On a balloon, no dot holds a privileged position. All dots see the others receding. All equally share the expansion. Likewise, in the cosmos, there is no true center, no cosmic origin point sitting in one special location. The Big Bang was not an explosion from a single spot into surrounding emptiness. It was the simultaneous expansion of all space everywhere. Every place was the beginning, and every place remains central to itself. Hubble's law captures this truth in numbers. The farther a galaxy is, the faster it recedes. Double the distance, double the speed. This simple relationship is a direct consequence of expansion. It is also the key that allows astronomers to measure the scale of the universe. By observing the redshift of galaxies and comparing it to their distance, we can map the cosmic expansion and trace its history. We can determine not only that the universe grows, but also how quickly and how that growth changes with time. What emerges is a story of acceleration. In the early universe, matter dominated. Its gravity slowed expansion, like a brake applied to a speeding car. But billions of years ago, another influence began to dominate. The energy of empty space itself, dark energy, began to push outward, overwhelming gravity's pull. Expansion, instead of slowing, began to accelerate. This discovery, made in the late 20th century, was as revolutionary as Hubble's first measurements. It means that the cosmos will not simply expand forever at a steady rate. It will expand faster and faster without end. This acceleration ensures that the observable universe will always be limited. As galaxies race away, more and more cross a threshold beyond which light can never reach us. Even if we build telescopes of unimaginable power, they cannot pierce this boundary. No instrument can capture what expansion hides. The horizon is written into the laws of physics. We can infer, imagine, and calculate what lies beyond, but we cannot see it. This realization is both humbling and liberating. Humbling because it reminds us of our limits, liberating because it invites us to think beyond observation. The expanding universe does not constrain imagination, it encourages it. If reality stretches beyond sight, then speculation is not folly but necessity. Theories of inflation, multiverses, and cosmic geometry all begin with the recognition that what we see is only a fraction of what exists. The impact of expansion is also deeply temporal. It means that the universe was once smaller, denser, and hotter than it is today. Rewind the cosmic movie, and galaxies crowd closer, temperatures rise, matter compresses. Rewind far enough, and we arrive at an origin, a moment when everything we see today was packed into a tiny volume. This is the Big Bang. It is not merely a theory, but a conclusion drawn from the observed expansion. If the cosmos expands today, it must have been smaller yesterday. Follow that logic, and the past converges upon a beginning. Yet expansion also opens questions about the future. If dark energy continues to dominate, galaxies will accelerate away, stars will burn out, and the universe will grow darker and colder. The expansion writes not only the past, but the fate of everything. It is a clock as well as a stage, ticking toward a future where all but the closest galaxies fade beyond reach. For us, living in this particular era, expansion is both gift and warning. It gives us the ability to see the universe in its vastness, to study galaxies billions of light years away, to detect the background radiation that preserves the memory of the Big Bang. But it also warns us that this visibility is temporary. In the distant future, the evidence will be gone, erased by expansion. We live in a privileged moment when the cosmos reveals its secrets. Future astronomers will inherit a quieter, lonelier sky. The expanding universe reshapes our identity. We are not beings in a static world, but participants in a story of endless growth. Our very existence is tied to the stretching of space, to the chain of events set in motion by expansion. Stars formed because matter clumped together before dark energy took over. Planets arose around those stars. Life emerged upon at least one of those planets. In this way, expansion is not an abstract fact. It is the reason we are here. And so, when we contemplate the expanding universe, we are not gazing at distant galaxies alone. We are gazing at the process that gave rise to us. The red-shifted light is not just a measurement, it is a message from the cosmos, telling us that we live within a grand unfolding, a universe that grows beyond sight, carrying us with it. As we follow this story further back, we encounter something even more astonishing than steady expansion. The universe did not begin expanding gently. It began with a burst of growth so rapid and so extreme that it dwarfs even the acceleration of today. This event, known as cosmic inflation, may explain the uniformity of the cosmos and the seeds of all structure within it. To understand the universe we see now, we must first understand this moment when expansion went wild. The concept of an expanding universe is not only a matter of observation, it is a doorway into a deeper understanding of reality itself. When Hubble measured the retreat of galaxies, he could not have known how profoundly his discovery would alter our place in the cosmos. His data showed that the farther away a galaxy is, the faster it recedes. That simple correlation revealed that expansion is uniform, that it happens everywhere, not from a single origin point. The universe does not grow from one central location. It grows in every direction at once. This truth is often misunderstood. People sometimes imagine the Big Bang as an explosion in empty space with matter flung outward from a central blast. But this is not what cosmology teaches. The Big Bang was not an event in space. It was an event of space. It was the sudden creation of the fabric of space-time itself, with every region expanding away from every other. In this sense, the Big Bang did not happen at a point. It happened everywhere. Every place in the cosmos is equally ancient, equally linked to that first moment of expansion. The redshift of galaxies is the clearest evidence of this ongoing growth, but it is not the only one. The cosmic microwave background, that faint radiation left over from the early universe, carries the imprint of expansion as well. Its uniformity across the sky tells us that space stretched to smooth out irregularities. Its faint fluctuations tell us how matter later clumped into galaxies. Without expansion, there would be no background radiation, no web of galaxies, no stars or planets. The universe as we know it is the direct consequence of expansion unfolding over billions of years. To picture the immensity of this, imagine winding the clock backward. The galaxies now separated by billions of light years would draw closer. The sky would grow brighter, hotter, denser. The cosmic background would shift from faint microwaves to glowing light, then to blinding radiation. At a few minutes after the beginning, the first atomic nuclei formed. At a few 100,000 years, the first atoms appeared. At hundreds of millions of years, the first stars ignited. All of this history is traced backward from the simple observation that galaxies today are receding. Expansion is the thread that connects the present cosmos to its fiery origin. But what if we wind the clock forward instead of backward? Expansion tells us what kind of future awaits. As galaxies accelerate away, the universe will grow colder and lonelier. The cosmic background will fade into undetectable wavelengths. The distant galaxies we now observe will vanish beyond the horizon. Even within our local group, stars will exhaust their fuel, collapse, or fade into embers. The expansion does not stop the cycle of birth and death, but it ensures that in the long future, darkness will prevail. The universe is not eternal in the sense once imagined. It has a past and it has a fate, both written by expansion. This understanding also places humanity in a remarkable position. We live in an epoch when the evidence of cosmic history is still available. We can measure the redshifts of countless galaxies, detect the background radiation, and piece together the story of origins. Billions of years from now, that evidence will be gone. Future civilizations, if they exist, may never know the truth. Their sky will tell them little of the Big Bang, little of expansion, little of the vast cosmos beyond their horizon. We live in the age of revelation, a fleeting window when the universe reveals its grandeur. The expanding universe is therefore not just a scientific concept but a philosophical one. It tells us that change is woven into the fabric of existence. It tells us that permanence is an illusion, that even the cosmos itself is a dynamic process. And it tells us that our knowledge, vast as it may seem, is temporary, a momentary glimpse into a universe that will one day hide its secrets once more. In contemplating expansion, we are compelled to ask deeper questions. What caused the universe to begin expanding in the first place? Why is dark energy accelerating it now? What lies beyond the horizon that expansion creates? These questions do not diminish science, they enrich it. They remind us that discovery is not a final act, but a continuing journey. The more we learn, the more horizons appear. And so, the expanding universe leads us forward into speculation. It hints that the story is not finished, that the universe we observe is only a fragment of something larger. To explain why the cosmos is so uniform, why it looks the same in every direction, and why the seeds of structure are distributed as they are, we must turn to the idea of inflation. This was a moment when expansion went far beyond the steady pace we see today, a moment when the universe grew unimaginably large in a fraction of a second. Inflation may be the reason our observable universe looks as it does, and it may hint that beyond what we see, the cosmos is even grander than we can imagine. Thus, the expanding universe, while astonishing on its own, is also a gateway. It leads us from observation into theory, from measurement into speculation. It tells us that the cosmos is growing, and it prepares us to consider how that growth began, in a burst so extreme that it set the stage for everything to follow. As we pass from the known into the speculative, we step into the realm of cosmic inflation, the endless stretch that may explain not only the universe we see, but the unseen realms beyond. The expanding universe, as revealed by Hubble, describes a steady growth, galaxies drifting apart over billions of years, space stretching like a rubber sheet. But when physicists followed this story back to its beginning, they encountered puzzles that steady expansion alone could not solve. Why does the universe look nearly the same in every direction, as if distant regions had once shared information, even though light could not have traveled between them in the time available? Why is the cosmos so flat, with no sign of the curvature expected from its enormous energy density? And why do we not see ancient relics of exotic particles or defects that should have survived from the early fireball? These questions seemed unanswerable within the framework of simple expansion. Then came a radical idea, first proposed in the early 1980s, that changed everything. Perhaps, in the first fraction of a second, the universe underwent a burst of growth far more extreme than the gradual expansion we see today. This event, called inflation, stretched the fabric of space by an unimaginable factor, smoothing out irregularities, flattening geometry, and diluting exotic relics into nothingness. In less than a trillionth of a second, the cosmos ballooned from subatomic size to macroscopic scales. Inflation solved puzzles not by tinkering with details, but by rewriting the history of the very beginning. To picture this, imagine an ant walking across a wrinkled balloon. At first, the surface is rough, filled with folds and bumps. But as the balloon inflates rapidly, those folds stretch flat. The ant experiences a smooth, nearly uniform surface. In the same way, inflation stretched the early universe, ironing out differences, leaving behind a cosmos remarkably even on large scales. That is why, when we observe the cosmic microwave background, we see nearly the same temperature in every direction. Inflation allowed distant regions to once be close enough to share conditions before being flung apart. The power of inflation is not only in smoothing, but also in seeding structure. Quantum fluctuations, the tiny jitter of energy inherent in the laws of physics, were stretched to cosmic scales during inflation. These fluctuations became the seeds of galaxies, stars, and planets. What began as microscopic uncertainty was inflated into macroscopic differences in density, later amplified by gravity into the cosmic web we see today. Without inflation, we would struggle to explain how such large-scale structure arose so naturally. The mathematics of inflation describe a field of energy that dominated the universe for a brief instant. This field, sometimes called the inflaton, acted like a spring wound tight with potential energy. When it released, it drove expansion at an exponential rate, doubling the size of the universe again and again in rapid succession. Then, in a transition known as reheating, the energy of the field poured into particles and radiation, creating the hot, dense plasma that marks the beginning of the Big Bang as we usually describe it. In this sense, the Big Bang was not the ultimate beginning, but the aftermath of inflation. What inflation tells us is staggering. Our observable universe, the sphere of 46 billion light-years radius, may be only a tiny patch of a vastly larger whole. Inflation could have stretched the cosmos far beyond what we can see, perhaps to scales infinite for all practical purposes. When we look at the night sky, we may be gazing at one bubble in an ocean of inflating space. The uniformity we observe is a local effect of an event that created realms vastly beyond our horizon. The evidence for inflation comes not from direct observation, but from its fingerprints. The smoothness of the cosmic microwave background, the flatness of cosmic geometry, the distribution of galaxies, all match the predictions of inflation. Subtle patterns in the polarization of the background radiation may carry further confirmation, though detecting them is extraordinarily difficult. Inflation remains a theory, but one with powerful explanatory power, uniting puzzles into a single sweeping answer. And yet, inflation also opens doors to speculation that reach far beyond the observable universe. If inflation occurred once, might it not occur again? Could regions of space still be inflating, spawning new universes like bubbles in a frothing sea? This idea, called eternal inflation, suggests that our cosmos is not unique, but one of countless others, each with its own laws, histories, and possibilities. Inflation, in solving puzzles of the early universe, may have revealed a multiverse beyond imagination. But before we leap to such speculation, it is worth pausing on the grandeur of the idea itself. Inflation transformed cosmology from a story of gradual growth to one of explosive birth. It turned the early universe from a puzzle to a coherent picture. And it left us with the humbling realization that what we call the observable universe is a minuscule fragment of a far greater reality. The endless stretch of inflation is the bridge between the cosmos we measure and the cosmos we imagine. From here, the journey leads naturally outward. If inflation stretched reality far beyond our horizon, then what lies in those unobservable realms? Are there galaxies like ours, stars like our sun, perhaps even other versions of ourselves? Or are those regions so distant and so strange that we cannot even guess their contents? Inflation invites us to ask not only how the universe began, but what exists beyond the limits of sight in the unobservable universe. Inflation is at once a scientific explanation and a source of wonder. To imagine the universe inflating in a fraction of a second is to grapple with numbers so vast they blur into the language of poetry. In less than 1/1,000,000th of a second, space expanded by a factor that may be written as 10 to the power of 26 or more. Such a leap is beyond direct human experience. It is like watching a speck of dust swell to the size of a galaxy before the blink of an eye has ended. In this inconceivably brief moment, the stage was set for everything that would follow. The very existence of such rapid expansion forces us to rethink what we mean by beginnings. The traditional view of the Big Bang imagines a singularity, a point where all matter and energy were compressed. Inflation suggests a different story. Instead of a singular point exploding, there was a field of energy filling space, driving expansion until it decayed into particles and radiation. What we call the Big Bang may be the afterglow of this transition. Not the ultimate origin, but the first act in a grander play. The strength of inflation lies in its explanatory reach. It smooths out the universe by stretching irregularities until they vanish. It flattens cosmic geometry by diluting curvature into invisibility. It explains the absence of exotic relics, like magnetic monopoles, by expanding them to such low densities that they are effectively non-existent. It seeds structure by magnifying quantum fluctuations. A single burst of expansion answers multiple mysteries with elegant simplicity. And yet, inflation is not a finished theory. Physicists debate what kind of field could have driven it, what energy scale it operated at, and how exactly it ended. Competing models exist, some predicting subtle differences in the patterns of the cosmic background. Searching for those patterns has become one of the great quests of modern cosmology. If detected, they would be the fingerprints of inflation, the smoking gun of that primordial event. But even without direct proof, the consistency between inflationary predictions and observation is striking. Few ideas in physics have transformed our understanding so completely. The philosophical implications are as profound as the scientific ones. Inflation implies that the universe we see is only a fragment of a much larger whole. If space expanded by such a staggering factor, then regions beyond our horizon are not only possible, they are inevitable. Our observable universe may be as small compared to the total as a single grain of sand is to all the beaches on Earth. What we call the cosmos may be just one patch in a quilt so vast it defies comprehension. Some versions of inflation go further still. They suggest that inflation never ends completely. While it halts in our region, allowing galaxies and stars to form, other regions continue inflating. In those regions, new bubbles of space may form, each with its own Big Bang, each with its own physical laws. This eternal inflation leads naturally to the idea of a multiverse, a cosmic sea in which countless universes arise and evolve. We cannot observe them directly, but inflation hints at their existence. If true, our cosmos is not the cosmos, but one among an endless variety. It is worth pausing here to feel the weight of this idea. The universe we know, with its hundreds of billions of galaxies, may itself be a tiny bubble in a boundless foam. Our horizon, vast as it seems, may be laughably small compared to the full reality. To stand beneath the night sky and realize this is to feel both humbled and exalted. Humbled, because our view is so limited. Exalted, because our minds can stretch beyond that limit, following the thread of theory into realms we will never see. Even if inflation does not prove eternal, its consequences for our universe alone are staggering. It means that everything we know, the Milky Way, the Sun, Earth, and life itself, exists because of fluctuations stretched during that brief, furious moment. Without inflation, there might be no galaxies, no stars, no planets, no humans to ponder these questions. Our very existence is tied to that first instant, to a process so brief we cannot truly imagine it, yet so powerful, it shaped everything. Inflation thus transforms cosmology from the study of what we see to the study of what we infer. It is a theory built not on direct observation, but on the coherence of explanation. It connects the smoothness of the sky to the vastness of the cosmos, the seeds of galaxies to the jitter of quantum energy. It is the bridge between the tiniest scales of physics and the largest scales of the universe. In this way, inflation embodies the unity of knowledge, the idea that the laws of nature, however strange, connect the smallest and the greatest in one story. As our instruments improve, as satellites measure the background radiation with ever finer precision, we may gather new evidence that strengthens or challenges inflation. But regardless of its final form, the idea has already reshaped our understanding. It tells us that the universe is larger than we can see, that the horizon is not the edge, but a veil, and that beyond it lies a reality more immense than we ever imagined. And yet, the question remains. If inflation stretched the cosmos beyond our sight, what lies in those unobservable regions? Are they like our universe, filled with galaxies and stars? Or are they strange realms where the laws of physics themselves differ? Inflation points us toward this question, but does not answer it. To follow the path further, we must step beyond what is observable, into speculation about the unobservable universe itself. Inflation may have lasted for only the briefest instant, yet its legacy is eternal. It set the stage for the cosmos as we know it, and it may have left behind realms forever beyond our perception. The numbers themselves strain comprehension. Space may have expanded faster than light during inflation, not because anything moved through space at that speed, but because the fabric of space itself was stretching. Distances doubled and redoubled in an exponential frenzy, so that regions once in contact were pulled apart beyond reach. This is why the sky looks uniform. Distant areas that should never have communicated in ordinary expansion were once close enough to share conditions before being swept away. The more closely we look at the cosmic microwave background, the more clearly we see the fingerprints of this event. The slight fluctuations in temperature, only 1 part in 100,000, match the predictions of quantum fluctuations stretched by inflation. These ripples are the seeds of all structure. Without them, the universe would be featureless, with no galaxies, no stars, no planets, no life. The existence of every human story traces back to that moment when quantum jitters were magnified into the scaffolding of the cosmos. Inflation is not only a theory of physics, it is the reason for the tapestry of existence. Yet the most breathtaking implication of inflation is that it may not have happened only once. In many models, inflation ends locally, in pockets of space, where the energy field decays into matter and radiation. But elsewhere, the field continues, driving inflation eternally. New bubbles of space continually form, each with its own Big Bang, each a universe unto itself. Our observable universe would then be just one bubble in a vast multiverse, a single wave in an infinite ocean. If this picture is true, then the reality we can see is only the smallest fragment of what exists. This possibility stirs both excitement and unease. If other universes exist beyond our own, they may follow different laws of physics. Some may contain no stars, no atoms, no chemistry to sustain life. Others may resemble ours so closely that they too give rise to galaxies and living beings. The multiverse, born from inflation, is not just a scientific idea but a philosophical challenge. It raises questions about uniqueness, meaning, and the scope of reality. Are we one of many, or one of one? Is our universe typical or exceptional? Inflation opens these questions without yet giving final answers. Still, it is crucial to remember that inflation is, at its heart, a scientific hypothesis, judged by evidence. The cosmic background radiation, the distribution of galaxies, the flatness of space, all lend it support. Yet direct proof remains elusive. Physicists search for patterns in polarization, for signals of primordial gravitational waves, for subtle imprints that would mark inflation beyond doubt. The quest is ongoing, and it may take generations to resolve. In the meantime, inflation stands as our best explanation for the early universe, a framework that unites observation with theory in a coherent whole. For us, standing on our small planet in one corner of a galaxy, inflation is a reminder of how far our minds can reach. We cannot witness the event directly, yet we can infer its existence from the faintest traces in ancient light. We cannot travel beyond the horizon, yet we can imagine what lies there, guided by the mathematics of physics. Inflation stretches not only space, but imagination. It reminds us that science is not confined to the visible. It extends into the realm of inference, of what must be true given what we see. And so we stand at a crossroads. The idea of inflation gives us confidence that the observable universe is not the whole story. It suggests a cosmos beyond sight, perhaps beyond comprehension. The next step in our journey is to follow that suggestion, to turn from the inflationary past to the unobservable present. If the universe is larger than we can see, what fills the space beyond our horizon? Are there galaxies, clusters, and stars beyond reach? Are there other universes entirely? Inflation points us toward these questions, and the unobservable universe awaits as the next chapter in our exploration. When we lift our eyes to the night sky, what we see feels like the totality of existence. The sweep of stars across the dark dome, the soft band of the Milky Way, the faint smudge of Andromeda, all combine to give the impression that the cosmos is laid bare before us. Yet everything visible to us, from the nearest star to the farthest galaxy glimpsed in deep surveys, lies within the boundary of the observable universe. Beyond that boundary, reality continues, but it is forever hidden. This hidden realm is not empty. It is filled with galaxies, stars, planets, and perhaps life, just as the region within our horizon is. The laws of physics do not suddenly end at the edge of visibility. They continue to operate, shaping matter and energy into familiar patterns. The only difference is that we cannot see it, and we never will. The expansion of space ensures that light from those regions will never reach us, no matter how long we wait. They are cut off not by walls, but by the growth of the cosmos itself. The idea that the universe extends beyond the observable is not speculation, but necessity. Imagine again the sailor on the endless sea. The horizon encircles them, but the ocean continues far beyond their sight. In the same way, the cosmic horizon surrounds us, but the universe extends far beyond its limit. Galaxies beyond the horizon are as real as those we see, though they are forever inaccessible. The observable universe is not the universe, but merely our patch of it. To appreciate the scale of this, recall that the observable universe is about 46 billion light-years in radius. That is already an incomprehensible distance, encompassing hundreds of billions of galaxies, each with billions of stars. Yet this vastness is only a fragment. If inflation occurred as we believe, the entire cosmos may be hundreds of times larger, or effectively infinite. Our visible sphere may be no larger in proportion than a grain of sand on a beach. The galaxies that lie just beyond our horizon are in some sense tragic figures. Their light may be streaming toward us, but space expands so swiftly that the light never arrives. The distance grows faster than progress can be made. Those galaxies are sealed away, their stories untold. And as expansion accelerates, more galaxies join them, crossing beyond the horizon, disappearing from sight forever. The unobservable universe is not a static realm, but a growing one, filled with more and more of the cosmos we can never know. For cosmologists, this raises both practical and philosophical challenges. On the practical side, it means that we can only ever test theories within our observable sphere. We cannot measure or map what lies beyond. Our knowledge is bounded by physics itself. On the philosophical side, it raises questions about meaning. If reality extends endlessly beyond sight, what is our place within it? Are we central or accidental, one patch among many? The unobservable universe forces us to confront the limits of knowledge and the humility of perspective. And yet, the idea of the unobservable is not a defeat for science. It is an invitation. By recognizing that what we see is not all that exists, we free ourselves from the illusion of completeness. We are reminded that maps are not territories, that knowledge is always partial. The unobservable universe beckons us to imagine, to consider possibilities beyond sight, to expand our thinking as the cosmos expands beyond our vision. In this hidden realm may lie galaxies like our own, perhaps countless copies of structures familiar to us. Or it may contain wonders we cannot conceive, shaped by the same laws of physics, but unfolding under conditions so different they defy analogy. The unobservable universe is both mirror and mystery, reflecting what we know and hiding what we do not. As we ponder it, we find ourselves drawn inevitably to the next question. If our observable universe is just a patch of a far larger whole, might there be other patches entirely separate from ours, with their own horizons, their own laws, their own histories? Inflation hints that this may be the case, that reality itself may consist of countless universes, each born from its own burst of expansion. To explore this possibility, we must step beyond even the unobservable universe and into the idea of the multiverse. The unobservable universe is a concept that reshapes our imagination. It is not a fantasy conjured from speculation, but a direct consequence of the rules of physics as we understand them. The speed of light is finite, the age of the universe is finite, and space itself expands. These three facts together guarantee that there is a limit to what we can see. And yet, nothing about these facts implies that the cosmos itself ends at that limit. Beyond it lies more universe, as real as our own, only hidden by distance and time. It is almost certain that galaxies populate those unreachable realms, galaxies as grand and varied as the ones we know. Stars must burn in their spirals and clusters. Supernovae must scatter heavy elements into space. Planets must form and circle. Perhaps some of those planets even harbor life, gazing up at their own skies and pondering the same questions we ask. For them too, a horizon surrounds their world, and beyond it lies an unobservable universe. Each vantage point is its own bubble of visibility, overlapping with others but never encompassing the whole. In this way, the cosmos is a mosaic of horizons. Each observer sees a slice of reality, framed by light and time. No single observer can see it all, yet together the pieces hint at the enormity of the whole. This vision is humbling. for it tells us that our knowledge is not absolute. We see less than we imagine, and what we do not see vastly outweighs what we do. The realization also alters how we think about destiny. As expansion accelerates, galaxies that we can see today will fade beyond the horizon tomorrow. The unobservable universe grows not because new galaxies form outside our view, but because existing galaxies cross the line of invisibility. The observable shrinks within the greater whole, like a candle flame in a darkening room. One by one, the farthest lights wink out, not because they end, but because they slip beyond reach. This slow vanishing is a reminder that our place in cosmic history is temporary, that we live in a rare epoch when the sky is still rich with evidence. And yet, even as galaxies disappear, the truth of their existence remains. Expansion does not annihilate them, it only hides them. In that sense, the unobservable universe is not an absence, but a presence beyond reach. It is filled with real matter, real energy, real events, happening in parallel with ours. We are connected to it not by sight, but by the common laws of physics, the shared history of inflation, and the Big Bang. This insight pushes us into the realm of philosophy. What does it mean to say that something exists if it can never be observed? Does reality require observation, or is it enough that physics tells us it must be there? In answering, most scientists take the latter view. The unobservable universe exists because its existence is a necessary consequence of the same laws that govern the observable. To deny it would be to deny the coherence of physics itself, and so the unobservable becomes not a contradiction, but an extension of knowledge. It is what lies beyond the map, drawn not with direct observation, but with inference. Just as ancient sailors knew that the sea extended beyond their horizon, so we know that the cosmos extends beyond ours. The unknown is not unknowable. It is a horizon of thought, a frontier where science and imagination meet. What lies in that frontier may astonish us. Perhaps there are regions where matter clumped differently, where galaxies formed earlier or later, where stars are brighter or dimmer. Perhaps the cosmic web stretches into patterns far stranger than the filaments we observe. Or perhaps those regions mirror ours so closely that they are indistinguishable, repeating the familiar on scales beyond comprehension. The unobservable universe may be a reflection, a variation, or a wild departure. We cannot know which, but we can embrace the vastness of possibility. As we contemplate this vast unseen realm, the question arises naturally: could there be not only more universe beyond sight, but other universes entirely? Could inflation, which stretched our cosmos to immense scales, also have spawned other bubbles with their own big bangs, their own physics, their own horizons? The step from the unobservable universe to the multiverse is not a leap of fantasy, but a continuation of logic. The cosmos beyond our horizon invites us to ask whether reality itself may be far larger than even the most generous imagination allows. The unobservable universe surrounds us like an invisible ocean. It is not a void of nothingness, but a continuation of the same reality we inhabit, filled with matter, energy, and perhaps even life, all beyond our sight. We know it must exist because the universe has no reason to end at the limits of our perception. The cosmic horizon is not a wall, but a boundary set by the finite age of the cosmos and the finite speed of light. Just as a traveler sees only so far across the sea, yet knows the waters extend beyond, so we too must accept that the universe continues past our view. This recognition forces us to face the limits of science. Astronomy is built on observation, yet the unobservable universe can never be measured directly. No telescope, no matter how powerful, will pierce the barrier of the horizon. This does not mean it is unreal. It means that our methods must adapt, that we must rely on theory and inference. We know the unobservable is there because the observable demands it. The smoothness of the cosmic microwave background, the distribution of galaxies, the very consistency of physical laws all point to a larger cosmos beyond sight. To deny it would be to assume that the universe ends abruptly at the edge of what we can see, an assumption that has no basis in physics. The unobservable also shapes how we think about ourselves. We often imagine that the universe we see is vast beyond measure, a stage of hundreds of billions of galaxies. Yet, if this is only a fraction, then our perspective is smaller still. We are not only a tiny planet around an ordinary star in an ordinary galaxy. We are observers trapped within a small bubble of light, surrounded by an ocean we cannot touch. This humbles us more deeply than any other realization. But humility is not despair. There is power in knowing our limits and wonder in imagining what lies beyond them. The unobservable universe invites us to stretch thought beyond evidence, to picture realities beyond reach. It challenges us to embrace both the rigor of science and the daring of imagination. It reminds us that knowledge is never complete, that horizons are always there to call us forward. The truth of the unobservable is also dynamic. As the universe expands, more and more galaxies slip beyond the horizon, joining the unseen. The unobservable grows, swallowing what was once visible. In the far future, nearly all galaxies will vanish from view, leaving only our local group. The cosmos will appear small and empty, though in truth it will be larger than ever. This fate highlights the privilege of our era. We live at a time when the sky is still rich with evidence, when the horizon still shows us galaxies near its edge. We are witnesses to a rare chapter in cosmic history, when the universe still reveals its grandeur. And so the unobservable universe is not a failure of vision, but a triumph of understanding. It shows us that science can reach beyond direct experience, that we can know what we cannot see. It teaches us that reality is larger than perception, and that humility and imagination must go hand in hand. Yet even as we contemplate this vast unseen realm, a deeper question arises. If the cosmos beyond our horizon is real, could there be other horizons entirely? Could inflation have created not just one universe but many, each with its own space, time, and laws of physics? The step from the unobservable universe to the multiverse is bold, but it flows naturally from the story we have told. Our horizon is not the end of reality. It may be the beginning of something far greater. In the next chapter, we turn to this possibility, exploring the idea that our universe is not alone, that inflation may have spawned countless others, each a bubble in a cosmic sea. The unobservable universe prepares us for this leap. If what lies beyond our horizon is real but forever hidden, then perhaps what lies beyond our universe is real as well, a frontier even more mysterious than the unobservable. The multiverse awaits. The unobservable universe already stretches our imagination, filling the unseen with galaxies and stars beyond reach. But some versions of inflation propose something even more radical. They suggest that our universe itself may not be the only one. Instead, there may exist countless other universes, each born from its own burst of expansion, each a bubble in a vast and eternal sea. This is the multiverse hypothesis, a vision of reality that multiplies the cosmos into a boundless ensemble. The idea begins with eternal inflation. In many models, the energy field that drove inflation does not decay everywhere at once. Instead, it decays in patches. In one patch, inflation ends, releasing energy into particles and radiation, igniting a Big Bang. In another patch, inflation continues, stretching space still further. Over time, these processes repeat, with new bubbles forming endlessly within the inflating background. Each bubble is a universe, separate from the others, cut off by the relentless expansion of space between them. Our observable universe is simply one bubble among many. To visualize this, imagine foam forming on the surface of boiling water. Each bubble is a separate region, expanding and shifting, sometimes colliding, sometimes remaining apart. The multiverse may be similar, an endless froth of universes born within a vast inflating medium. Each bubble has its own space and time, its own cosmic history. Some may be lifeless voids, others may sparkle with galaxies and stars. Perhaps some even host beings who, like us, wonder about what lies beyond their horizon. The multiverse idea does not stop with eternal inflation. Another source lies in quantum physics, specifically the many worlds interpretation. According to this view, every quantum event, every branching of possibility produces new universes. In one universe, a particle goes left. In another, it goes right. In one, a star collapses. In another, it does not. Every possibility is realized in some universe, creating a branching tree of realities. The cosmos, then, is not one story, but every story, all happening at once in parallel worlds. String theory, the attempt to unify all forces of nature into a single framework, offers yet another path to the multiverse. The theory allows for a vast landscape of possible configurations, each corresponding to a different set of physical laws. If inflation populates this landscape, then different universes may realize different laws of physics. Some may have stronger gravity, others weaker. Some may lack the chemistry needed for life, others may team with it. In this view, the multiverse is not only many in number but diverse in nature, a cosmic library containing every possible law of reality. These visions are bold, but they are not without foundation. The same mathematics that explain the observable universe, the same physics that describe inflation and quantum mechanics, lead naturally to the idea of many universes. The multiverse is not an invention of fantasy, but a consequence of theories already in play. And yet, it is also controversial, because by definition, these other universes may be forever beyond observation. If science depends on evidence, how can we test what lies outside our universe? Some argue that we cannot. Others suggest that indirect clues may exist. If our bubble universe once collided with another, perhaps the scar of that collision lingers in the cosmic microwave background. If the laws of physics vary across the multiverse, perhaps we can explain why ours seems so finely tuned for life. The multiverse could answer one of the greatest mysteries. Why do the constants of nature allow stars and planets and chemistry? Perhaps it is not design, but selection. In most universes, conditions forbid life. In a few, like ours, conditions permit it, and only in such places can observers arise to ask the question. The multiverse thus reshapes not only science but philosophy. It challenges our sense of uniqueness, our longing for centrality. If countless universes exist, then we are not only not at the center of the cosmos, we are not even unique within reality itself. We are one of many, perhaps infinitely many, each telling its own story. At first, this may feel diminishing, but it also expands our vision. The multiverse, if true, means that reality is richer than we could ever dream, that existence is not one note, but an infinite symphony. Whether or not the multiverse exists remains an open question. The idea may forever hover at the edge of science, tantalizing but unprovable, and yet it is worth contemplating, for it grows naturally from what we know. Inflation, quantum mechanics, and string theory all point toward it. Perhaps one day, indirect evidence will tilt the balance, perhaps not. But the multiverse reminds us that the cosmos is not obliged to be simple, or finite, or within our grasp. It is what it is, vast beyond imagination, and our task is to follow its hints wherever they lead. The multiverse is the boldest step yet beyond the observable. It takes us from galaxies beyond sight to universes beyond comprehension. And yet, even here, we are not left entirely without clues. The next step in our journey is to ask how we might search for traces of these other realms. Are there marks upon the sky, anomalies in the background, flows of galaxies that whisper of collisions with other universes? The quest for such evidence is our way of reaching across the horizon, of listening for echoes from the infinite beyond. The idea of a multiverse is at once thrilling and unsettling. It suggests that our universe, vast as it seems, is but one among countless others. To truly grasp this, we must set aside the comfortable thought that the cosmos we observe is the totality of existence. Instead, we must imagine a grander stage, one where many universes coexist, each sealed from the others, each telling its own story. Consider first the vision offered by eternal inflation. In this picture, space is like a field forever bubbling with new beginnings. Inflation halts in some regions, giving rise to universes like ours, while continuing in others. The result is a fractal-like sprawl of bubbles within bubbles, each expanding into its own realm. Between them lies inflating space that grows faster than the bubbles can collide. Our universe may be one such bubble, floating in an endless froth. The sheer abundance implied here is staggering. There could be not only billions of universes, but numbers so large they defy any measure, each with its own version of cosmic history. Now consider the many worlds interpretation of quantum physics. Here the multiverse is not spatial, but branching. Every quantum decision splits reality, creating parallel universes that follow each possible outcome. In one branch, a star collapses into a black hole. In another, it remains stable for millions more years. In one branch, a species evolves intelligence. In another, it does not. According to this view, the multiverse is not a place, but a process, a constant branching of possibility. If correct, then every choice, every fluctuation, every event has produced countless parallel realities, each as real as our own. The version suggested by string theory goes further still. If the theory is right, then the universe allows a near infinite number of possible configurations, each defined by different shapes of extra dimensions, different values of physical constants. Inflation could populate these possibilities, creating universes where the laws of nature themselves differ. Some universes may have no atoms. Some may lack gravity strong enough to bind stars. Some may be hostile to complexity, and a few, like ours, may allow the chemistry of life. The multiverse becomes not just a repetition of universes, but a diversity of realities, each with its own rules. This framework also offers an answer to one of the deepest mysteries: why the laws of physics in our universe are so finely tuned for life. The strength of gravity, the charge of the electron, the energy of empty space, all fall within narrow ranges that permit stars, planets, and chemistry. If they were even slightly different, life as we know it could not exist. Why should nature be so fortunate? The multiverse offers a simple explanation. In countless universes, the constants take on different values. In most conditions, forbid life. In a few, conditions allow it. We exist in one of those few, because only there could beings like us emerge to ask the question. This is a profound shift in perspective. Instead of asking why the universe is tuned for life, we ask why we find ourselves in this universe. The answer becomes anthropic. We are here because only in such a universe could we exist. It is not design nor coincidence, but selection. The multiverse reframes the mystery from why these laws to which universes permit observers. But the multiverse also challenges science itself. If these other universes are beyond observation, how can we test the idea? Some physicists argue that the multiverse lies outside the bounds of science. Others contend that indirect evidence may exist. Perhaps collisions between bubble universes left imprints in the cosmic microwave background. Perhaps unusual flows of galaxies are caused by gravitational pulls from realms beyond our own. Perhaps the apparent fine-tuning of our universe is itself a clue, pointing to a larger ensemble. The debate is not settled, but it is active, and it shapes the frontier of cosmology. The multiverse, therefore, sits at the boundary of knowledge. It is not proven, but neither is it fantasy. It is a possibility born from serious theories, a vision consistent with what we know, even if it may remain forever untestable. For now, it is a hypothesis, bold and humbling, reminding us that the cosmos may be far greater than the bubble of space we inhabit. As we reflect on this, the question becomes one of evidence. If other universes exist, can we ever hope to detect them? Could the scars of collisions, the anomalies in background radiation, or the patterns of cosmic flows whisper of their presence? In the next stage of our journey, we turn to the search for such clues, examining whether the multiverse has left faint fingerprints upon the universe we can observe. The multiverse, if real, is not just a scientific proposal, but a philosophical upheaval. It forces us to confront the possibility that our universe, vast as it seems, is neither unique nor privileged. Instead, it is one instance among countless others, each a separate cosmos with its own laws and histories. The very word universe, once meaning all that exists, would need to be redefined. Reality would be larger than the universe itself. For many, this idea is unsettling. It seems to rob our cosmos of uniqueness, to reduce it from everything to one among many. Yet another way to see it is as an expansion of wonder. The night sky already humbles us with its immensity, but the multiverse multiplies that immensity beyond measure. Instead of one grand story of existence, there may be countless stories, an infinite library of realities. Our universe is a single book, beautiful and vast, but part of a collection so immense that no shelf could hold it. Some physicists resist the multiverse, not out of denial, but out of caution. They remind us that science rests on observation, and that the multiverse may lie forever beyond it. To speak of unobservable universes may risk leaving science behind. Yet others argue that science has always extended itself beyond the immediately visible. We infer atoms, though we cannot see them directly. We infer black holes through their influence on nearby matter. In the same way, we may infer the multiverse through the traces it leaves upon our universe, through the logic of fine-tuning, through the consistency of inflationary models. The debate is far from settled. Some embrace the multiverse as a natural outcome of current theories. Others see it as speculation bordering on philosophy. Yet both groups agree on one thing. The multiverse is a possibility worth considering, for it flows not from imagination alone, but from the mathematics of physics itself. It is a hypothesis born from the very effort to explain why our universe is the way it is. For us, contemplating the multiverse is both exhilarating and sobering. It suggests that our universe, with its galaxies and stars, is not the whole of reality, but one island in an endless sea. It suggests that the laws of physics, which feel universal, may be local customs of our particular bubble. It suggests that existence itself is richer and stranger than any single cosmos could contain. And yet, even if the multiverse is real, we remain bound to our own universe. We cannot escape our bubble, cannot step across into another. Our horizon remains our prison, but also our window. What we can do is search for hints. If other universes ever touched ours, perhaps the mark of that encounter lingers in the microwave background, in strange cold spots or unusual alignments. If they exert gravitational pulls, perhaps large-scale flows of galaxies whisper of their presence. If fine-tuning demands an explanation, perhaps the multiverse provides it. These are the clues we can pursue, the echoes of other universes within our own. So the multiverse, whether provable or not, reshapes our vision. It teaches us that reality may be layered, that the observable universe is but the surface of something deeper. It reminds us that humility is the proper stance before the cosmos. And it inspires us to seek evidence, however faint, that we are not alone in the grandest sense. The story does not end here. Having explored the possibility of other universes, we now turn to the search for their traces. Are there bruises on the sky from ancient collisions? Are there flows in the cosmic web that reveal influences beyond our horizon? In the next chapter, we shift from speculation to pursuit, from theory to the hunt for evidence. The multiverse may or may not exist, but the search for clues is itself a journey of wonder. The idea of other universes is bold, but science demands more than boldness. It demands evidence, or at least the hope of evidence. If our universe is just one bubble among many, if realms beyond our horizon exist, might they have left faint marks upon the cosmos we can see? The search for such marks has become one of the most fascinating quests in modern cosmology, blending observation, theory, and imagination. The first and most important tool in this search is the cosmic microwave background, the ancient light released when the universe was only a few 100,000 years old. This glow is the oldest image we can ever hope to capture, a photograph of the universe in its infancy. Tiny fluctuations in its temperature record the seeds of galaxies, the fingerprints of inflation, and perhaps, just perhaps, the echoes of other universes. If our bubble ever collided with another, the scar of that impact might remain. It would appear as an anomaly, a region of the sky slightly cooler or warmer than expected, a bruise left by a cosmic encounter. One such anomaly has drawn particular attention, the so-called cold spot. Discovered in maps of the microwave background, it is a region larger and colder than theory predicts. Some scientists suggest it may be a statistical fluke, a random fluctuation in the primordial soup. Others propose it might be caused by a vast void of galaxies in that direction, a region underdense enough to leave an imprint on passing light. But a few suggest something more radical, that the cold spot is the mark of a collision with another universe, a bruise from a bubble brushing ours in the earliest moments of time. This idea is not proven, but it shows how the search for clues proceeds. We look for anomalies, for patterns that standard models cannot easily explain. The cold spot may yet prove to be nothing extraordinary, but the very act of searching pushes us closer to the boundary between observation and speculation. It reminds us that our universe may carry faint whispers of contact with realms beyond. Other hints may come from large-scale flows of galaxies. In recent years, astronomers have studied the motion of galaxy clusters across hundreds of millions of light years. Some data suggested that clusters were drifting in a common direction, as if pulled by a gravitational influence beyond the observable universe. This so-called dark flow sparked excitement, with some interpreting it as the tug of mass from another universe. Later, analyses questioned the evidence, and the debate continues. But even the possibility that distant structures could feel the gravity of unseen realms stirs the imagination. The search for clues is not limited to specific anomalies. It also includes the overall geometry and structure of the universe. If our cosmos were finite but wrapped upon itself, we might see repeating patterns in the microwave background, circles that match as if the universe folded back upon itself. If our universe once collided with another, we might detect circular features left in the early light. If dark energy behaves differently than expected, it might hint at interactions with physics beyond our universe. Each of these avenues is speculative, yet each is grounded in observation, in the idea that the universe might reveal more than it seems. For now, no single piece of evidence compels us to accept the multiverse. The cold spot remains unexplained, the dark flow uncertain, the repeating patterns absent. But the very act of looking matters. It shows that science is willing to test bold ideas, to confront speculation with data, to explore the frontier where the observable touches the unobservable. The search for clues is not a distraction, but a necessity. Without it, the multiverse would remain pure theory. With it, the possibility of evidence remains alive. And beyond the search for direct marks, there is the indirect reasoning of fine-tuning. The laws of physics in our universe appear delicately balanced for complexity. The strength of gravity, the energy of empty space, the masses of particles, all fall within narrow ranges. Why should this be so? One explanation is coincidence, another is design. The multiverse offers a third. In countless universes, the constants vary, and only in those where conditions permit complexity does life arise to ask the question. Fine-tuning, then, may itself be a clue, an indirect pointer to a larger reality. Whether we find direct scars or not, the search changes how we see the universe. It reminds us that our cosmos may not be self-contained, that it may bear the echoes of events beyond its borders. It encourages us to keep probing, to refine our instruments, to search the sky with sharper eyes. The possibility of other universes may or may not be confirmed, but the search for evidence will always enrich our understanding of the one we inhabit. As we follow this path, we find that the search for clues does not stop with collisions or anomalies. It extends to the very shape of the universe itself. The geometry of space may hold secrets about what lies beyond, whether the universe is infinite or finite but unbounded, whether it stretches forever or folds back upon itself. To explore the geometry is to take the next step, to ask not only whether other universes exist, but what shape our own reality truly takes. The search for signs of other universes is a journey at the edge of science, where evidence is faint and interpretation delicate. Yet even here, astronomers and physicists pursue the hunt with rigor, for the rewards of discovery would be extraordinary. To find proof of another universe would be to expand reality itself, to confirm that what we call the cosmos is only a small part of a much larger whole. The cosmic microwave background remains the prime arena for this search. Its faint glow is a canvas painted with the earliest strokes of cosmic history. On that canvas, scientists look for subtle features that might betray contact with other realms. Circular imprints, unexplained alignments, or unusual patches of hot and cold may all serve as hints. The cold spot is the most famous, but there are others. Curious alignments of fluctuations known as the axis of evil, and hemispherical asymmetries that challenge the assumption of perfect uniformity. None are definitive, but each keeps the door ajar. The possibility of bubble collisions is especially intriguing. If our universe expanded as a bubble in an inflating sea and another bubble formed nearby, the two might have collided. The energy of that impact would ripple through space, leaving a scar on the microwave background. Detecting such a scar would be like finding a fossil from an event before the dawn of time. It would prove that our universe is not alone, that others exist, and that the multiverse is more than theory. Teams of scientists have scoured the data for such features. So far, the evidence remains inconclusive, but the search continues with every new map of the sky. Other searches extend to the distribution of galaxies across cosmic scales. If another universe exerted gravitational influence on ours, perhaps through regions of overlapping inflation, we might detect it in the peculiar motions of galaxies. The idea of dark flow grew from this possibility. Observations once suggested that clusters of galaxies were drifting together at unusual speeds, as if tugged by mass beyond the observable horizon. Later studies questioned the strength of the signal, and debate continues. If confirmed, dark flow could be a whisper of hidden realms. If not, it is still a reminder of how sensitive our tools must be when listening for faint cosmic voices. Beyond collisions and flows, scientists explore more subtle avenues. Some propose that quantum entanglement might reach across universes, leaving faint imprints in particle behavior. Others suggest that the properties of dark energy might encode information about interactions with other realms. These ideas remain speculative, but they show the creativity of the search, the willingness to look wherever a hint might appear. Perhaps the most compelling indirect evidence comes not from anomalies, but from necessity. The fine-tuning of physical laws in our universe is striking. Gravity is just strong enough to form stars, but not so strong as to collapse them instantly. The energy of empty space is small enough to allow galaxies, but not large enough to tear them apart. The constants of physics fall into ranges that seem improbably suited to life. Why should this be so? One answer is the multiverse. If countless universes exist, each with different laws, then it is not surprising that one would permit life. We exist in that one because only there could observers arise. This reasoning, known as the anthropic principle, is controversial. but it offers a way to connect the multiverse to the evidence of our own existence. Still, caution is necessary. Many anomalies in the sky have been proposed as signs of other universes, only to fade under closer scrutiny. The cold spot may yet be a statistical fluctuation. The axis of evil may vanish with better calibration. Dark flow may dissolve into noise. Science thrives on skepticism, and every claim must withstand rigorous testing. The absence of confirmation does not disprove the multiverse, but it reminds us that extraordinary claims demand extraordinary evidence. Yet even if the multiverse remains unproven, the search itself enriches cosmology. It sharpens our tools, deepens our understanding of the microwave background, and refines our measurements of galaxies. It keeps us alert to the possibility that the universe may hold surprises, that reality may be stranger than we imagine. The search for clues is not a side quest, but a central pursuit, a way of pressing against the horizon of knowledge. In the end, the search reminds us that science is as much about questions as answers. To ask whether we can find evidence of other universes is to acknowledge the limits of sight and the vastness of possibility. Whether the clues prove real or not, the act of searching honors the spirit of exploration. It keeps alive the wonder that first led humanity to look up at the stars and wonder what lies beyond. The next step takes us from evidence to structure. Even if we cannot yet confirm other universes, we can ask what the geometry of our own universe tells us. Is it flat, open, or closed? Infinite or finite, but unbounded? The shape of space itself may hold secrets about what lies beyond our horizon, and exploring that geometry brings us closer to understanding the true nature of reality. The search for traces of other universes pushes our instruments and our imagination to their limits. We have learned to read the faintest patterns of light, to measure fluctuations no greater than 1 part in 100,000, and to chart the drift of galaxies across immense distances. These efforts reveal a cosmos rich with structure, but they also remind us of how fragile evidence can be. A signal that looks like a clue today may vanish under closer inspection tomorrow. Still, the act of searching matters. It transforms the multiverse from pure philosophy into a testable question, even if the tests are indirect and uncertain. Consider again the cold spot. If it is truly a collision scar, then our universe once brushed against another, leaving a permanent mark on the oldest light in existence. That would mean we have already glimpsed the multiverse, not through direct sight, but through its aftermath. Yet it may be only a statistical quirk, a reminder that randomness can mimic meaning. This tension between possibility and caution defines the frontier of cosmology. We yearn for proof, but we must be patient with doubt. The same is true of the axis of evil, the strange alignment of fluctuations in the microwave background along a preferred direction. Some see in it a hint that our universe is not perfectly isotropic, perhaps influenced by realms beyond. Others see an artifact of measurement, a ghost of calibration. The debate illustrates the challenge of interpreting anomalies. The universe is vast, data sets are immense, and chance can always produce patterns that tempt explanation. The true test is whether such patterns persist as instruments improve. Dark flow, too, embodies this ambiguity. If galaxy clusters drift under the pull of unseen mass beyond our horizon, then we are already feeling the gravity of the unobservable universe. That would be direct, though indirect evidence that reality extends beyond sight. But if the signal is noise, then the search must continue elsewhere. Either way, the quest forces us to refine our tools, to measure motions with ever greater precision. Even null results deepen our knowledge, for they set limits on what is possible. In this sense, the search for clues is valuable even without confirmation. It teaches us humility before the data, patience with uncertainty, and openness to surprise. It keeps alive the possibility that the universe may reveal more than we expect, that a faint anomaly may one day grow into a profound discovery. Science advances not only by answers, but by the persistence of questions, by the willingness to follow hints wherever they lead. And beyond the anomalies, there remains the puzzle of fine-tuning. The very fact that we exist, that stars burn steadily, that chemistry flourishes, demands explanation. The multiverse offers one answer, and though it is indirect, it is powerful. If reality contains countless universes, then we should not be surprised to find ourselves in one where conditions permit life. The alternative is to assume an improbable coincidence or a deeper principle we have not yet uncovered. Either way, the mystery compels us to look further, to search not only the sky, but the laws of physics themselves for clues. The search for evidence of other universes therefore reflects the essence of cosmology. It blends observation with theory, skepticism with imagination. It acknowledges limits, but refuses to stop at them. It seeks to test even the boldest ideas, not with blind belief, but with careful measurement. In doing so, it expands our sense of what science can be. It shows that even questions once thought unanswerable can be approached, if not resolved, through the steady accumulation of evidence. And yet, as important as the search for other universes may be, it also points us back to our own. For in seeking scars of collisions or traces of distant pulls, we are also learning about the structure of our cosmos. We are mapping its geometry, probing its expansion, measuring its energy. These efforts tell us not only what might lie beyond, but what our own universe truly is. The search for others sharpens our picture of ourselves. As our journey continues, we leave behind the search for faint scars and turn toward the broader question of shape. The geometry of the universe may itself hold clues about the infinite or the finite, the open or the closed. Is the cosmos flat, stretching forever? Is it curved, wrapping back upon itself? Or is it shaped in ways our minds can barely conceive? The next chapter will explore these questions, for to understand the geometry of space is to glimpse the architecture of reality itself. For most of human history, the universe was imagined as a vast dome, a celestial sphere surrounding the Earth. The stars appeared fixed upon it, the heavens arching overhead like the inside of a grand shell. Even after we learned that Earth orbits the Sun and that the stars are suns in their own right, the mind still clung to the idea of a cosmic edge, a boundary where everything might stop. Yet modern cosmology teaches something stranger and subtler. The universe may have no edge at all, not because it is infinite in the simple sense, but because its geometry allows it to be finite without boundaries, or flat and endless, depending on its shape. To understand this, imagine standing on the surface of a balloon. For the tiny creatures that live on the balloon, there is no edge, no cliff where the surface ends. They can walk forever, circling endlessly, yet the surface is finite. It is two-dimensional, but curved into a higher dimension. The universe could be similar, except in 3 dimensions. It could be finite, but without boundary, curving back upon itself. In such a cosmos, if you traveled far enough in one direction, you might eventually return to your starting point, not because you crossed an edge, but because space itself is wrapped around. The alternative is that the universe is flat, not curved, stretching without limit in every direction. In a flat cosmos, space extends forever, infinite in extent. Galaxies continue without end, the cosmic web stretching into eternity. Both possibilities are allowed by Einstein's general theory of relativity, which ties the geometry of space to its energy content. Whether the universe is open, closed, or flat depends on how much matter and energy it contains and on the role of dark energy in driving expansion. For decades, cosmologists have sought to measure this geometry, to weigh the universe and determine its shape. They have done so by observing the cosmic microwave background, which serves as a kind of cosmic ruler. The size of the fluctuations in that ancient light is known, and by comparing their apparent size on the sky, we can infer whether space bends inward, outward, or not at all. The results are striking. Observations show that the universe is flat to a remarkable degree, with any curvature so small it is beyond current detection. This flatness raises questions. Inflation provides an elegant answer, stretching space so vast that any curvature is smoothed away, leaving a cosmos indistinguishable from flat on scales we can observe. But if the universe is truly flat, then it may be infinite. And if it is infinite, then beyond the observable horizon, galaxies continue forever. In such a universe, the unobservable is not just larger than the observable, it is endless, a sea without shore. Yet if the universe is only nearly flat with a slight curvature, then it could still be finite, wrapping back upon itself like the surface of a sphere. In that case, space would be immense but bounded, containing a finite number of galaxies. The distinction between infinite and finite but unbounded is subtle but profound. One leads to endless repetition, the other to closure without edges. Our measurements cannot yet decide between these possibilities with certainty. The observable universe is too small a sample of the whole. If the cosmos is finite, its size may be much larger than the horizon, making curvature undetectable. If it is infinite, then by definition we can never see its end. The geometry of the universe thus remains one of the deepest mysteries, one that ties together observation, theory, and imagination. Whether infinite or finite, the implications are staggering. If infinite, then every arrangement of matter must occur somewhere, repeated endlessly across space. There would be other galaxies identical to ours, other Earths identical to this one, even other versions of ourselves pondering the same questions. If finite, then the cosmos is still unimaginably vast, a closed system where everything is connected, but without edge or center. Both possibilities defy ordinary intuition, and both remind us that the true shape of the universe may lie forever beyond direct grasp. The geometry of space is not just an abstract question. It shapes the destiny of the cosmos. A closed universe might once have implied eventual collapse, though dark energy now changes that fate. A flat or open universe expands forever. Geometry is the skeleton of cosmic history, determining not only the size, but the future of reality. And so we are left with a paradox. We can measure the universe with exquisite precision, yet the ultimate shape of space may remain unknowable. The horizon limits our view, hiding whether the cosmos bends or stretches endlessly. This paradox is not a failure, but a reflection of our place within the whole. We are creatures within the universe, unable to step outside and see it from beyond. We must infer its shape from within, using light and theory as our guides. The question of geometry leads naturally to a deeper one. If the universe has no edge, then what lies beyond it? If it is infinite, what does infinity truly mean? If it is finite but unbounded, what does it mean to live in a cosmos that has no outside? These questions blur the line between science and philosophy, and they draw us into the heart of the mystery. The question of geometry is not simply about lines and curves, it is about the very architecture of reality. When we say the universe is flat, open, or closed, we are not speaking of shapes in the ordinary sense, but of how space itself behaves when stretched across cosmic scales. The rules of geometry that schoolchildren learn with rulers and triangles are transformed when applied to the universe as a whole. Imagine drawing a giant triangle across the heavens. In Euclidean geometry, the kind familiar to us, the angles of a triangle always add up to 180 degrees. But in a curved universe, the sum would be different. On the surface of a sphere, for example, triangles can have angles greater than 180 degrees. On a saddle-shaped surface, they can sum to less. If we could trace such cosmic triangles using the light of galaxies as markers, their angles would reveal the curvature of space. Astronomers cannot draw such literal triangles, but they can use the cosmic microwave background as a proxy. The ripples in that ancient light have a characteristic scale, like fingerprints imprinted on the early universe. By measuring their apparent size across the sky, we learn whether space bends inward, outward, or remains flat. The verdict, within tiny margins of error, is that space is flat. Yet here lies the subtlety. Flatness may mean infinite extent, but it could also mean a very large but finite cosmos, whose curvature is too slight to detect. In other words, our instruments may be sampling only a tiny piece of a far grander structure. The idea of a finite but unbounded universe is among the most difficult for human intuition. We are accustomed to edges, to beginnings and ends. A road stops at a cliff, a book stops at its final page. But in curved space, edges are unnecessary. Just as a traveler can walk endlessly around Earth without finding an edge, so too might the universe wrap upon itself. In such a cosmos, a photon of light could, in principle, circle the universe and return to its origin, though expansion would likely prevent it in practice. The absence of boundaries does not mean the absence of limits. It means the limits are woven into space itself. An infinite universe, by contrast, carries its own philosophical weight. Infinity is not merely very large, it is without bound, without repetition, without closure. If space is truly infinite, then there are infinite galaxies, infinite stars, infinite arrangements of matter. Somewhere, in the vastness, there must be galaxies indistinguishable from our own, planets identical to Earth, even beings identical to us, pondering the same thoughts. Infinity implies repetition, not because the universe seeks to copy itself, but because infinite possibilities allow every configuration to occur. This is not speculation beyond mathematics. It is the logical consequence of unending extent. Whether finite or infinite, the implications are staggering. A finite but unbounded cosmos is a grand loop, a closed system without edge, containing everything in a vast yet measurable whole. An infinite cosmos is an endless sea, where our observable patch is but a grain of foam. Both pictures challenge the imagination, both dissolve the comforting idea of boundaries, and both emerge naturally from Einstein's general theory of relativity. The geometry of the universe also shapes its fate. In earlier eras of cosmology, a closed universe implied eventual collapse, a cosmic Big Crunch that would mirror the Big Bang. An open universe implied eternal expansion, a gradual thinning into cold emptiness. Flatness balanced precariously between the two. But the discovery of dark energy shifted these destinies. Regardless of geometry, accelerated expansion ensures that the cosmos will not collapse, but will continue stretching into the far future. Geometry still matters, but destiny is now tied to the mysterious push of dark energy. In contemplating geometry, we are reminded again of the limits of observation. We can measure curvature with exquisite precision, but we cannot see beyond the horizon. The ultimate shape of the cosmos may forever elude us, hidden by distance and time. Still, our measurements tell us that whatever the full truth, the universe is unimaginably vast, far larger than the observable patch we inhabit. The mind resists these ideas, for we are creatures evolved to live on plains and mountains, to think in straight lines and small distances. To imagine space folding upon itself, or stretching endlessly, is to step beyond instinct into abstraction. Yet abstraction is the tool that science offers us, a way to glimpse the unseen through the logic of mathematics and the evidence of light. And beyond geometry lies an even deeper question. If the universe is finite but unbounded, what does it mean that there is no outside? If it is infinite, what does it mean for infinity to be real, not as a number, but as a physical fact? To pursue these questions is to push science into philosophy, to ask not only what shape the universe takes, but what that shape means for reality itself. The geometry of the universe is more than a matter of abstract mathematics. It is a key that may unlock our deepest questions about what lies beyond. A flat universe, stretching endlessly, suggests infinity, while a closed universe, curving back upon itself, suggests finitude without boundaries. Both are strange, both are possible, and both force us to think in ways far removed from daily experience. If the universe is infinite, then every possible arrangement of matter must occur somewhere. That means not only galaxies and stars repeating, but entire worlds repeating as well. In an infinite cosmos, the combinations of atoms are finite, but the number of locations to arrange them is unending. Inevitably, repetition occurs. Somewhere, unimaginably far away, there could be a planet identical to Earth, with people identical to us living out the same histories. And beyond that, infinite variations. This is not a flight of fancy, but a logical extension of infinity itself. If the universe is finite but unbounded, then the picture is subtler. There may be no repetitions, no infinite copies, but instead, a grand wholeness that circles back upon itself. The absence of edges means there is no outside to the cosmos, no beyond. Asking what lies beyond would be like asking what lies north of the North Pole. The answer is that the question dissolves. The universe is all there is, complete in itself, vast yet closed. This view is no less humbling, for it forces us to accept that our sense of edges and boundaries is shaped by life on a small planet, not by the architecture of reality. Einstein's equations allow both possibilities, but our instruments lean toward flatness. Still, even perfect flatness may not mean infinity. Inflation can stretch curvature so smooth that the observable patch looks flat, even if the full cosmos is finite. In this sense, geometry remains uncertain. It is as if we are ants on a vast surface, able to measure only a small region, unable to see enough of the whole to know its true form. This uncertainty is not failure. It is the mark of science confronting limits. We cannot step outside the universe to view its shape, but we can infer it from within. And what we learn is that whatever the ultimate geometry, the universe is larger than we can imagine. The observable cosmos, vast as it is, may be only the smallest fraction of a far greater whole. Geometry also connects to destiny. A closed universe once implied eventual collapse. An open universe, eternal expansion. Today, with dark energy driving acceleration, collapse is unlikely regardless of curvature. Yet geometry still matters, for it shapes how galaxies form, how cosmic history unfolds, how the future stretches into time. The skeleton of space is written into every star and every cluster, woven into the very fabric of existence. And so, as we consider the geometry of the universe, we are led to a final reflection. If there is no edge, then what lies outside becomes meaningless. If the universe is infinite, then beyond is only more of the same. If it is finite but unbounded, then beyond does not exist. In either case, our intuition falters, but our imagination expands. The question of geometry is not merely about lines and curves. It is about the meaning of space itself, and about what it means to live within a cosmos that may have no outside at all. From here, our journey shifts from space to time. If the geometry of the universe raises questions of where and what, the nature of cosmic time raises questions of when and how. Beyond our horizon, time may unfold differently, ages may vary, and the arrow of entropy may take forms we cannot see. To understand the cosmos fully, we must turn not only to the shape of space, but to the flow of time itself. When we look out at the universe, we are not only looking across space, we are looking back through time. The light of distant galaxies has traveled billions of years to reach us, carrying with it a record of the past. The farther away we gaze, the younger the cosmos appears. A galaxy 10 billion light-years distant is seen as it was 10 billion years ago. The cosmic microwave background shows us the universe when it was only a few 100,000 years old. Our telescopes are time machines, revealing not the universe as it is now, but as it was then. This truth deepens when we consider horizons. Beyond the observable universe, time itself becomes a mystery. We cannot know how old distant regions are, or how they have evolved. We cannot even assume that time flows there as it does here. Einstein's relativity teaches that time is not absolute, but woven with space into space-time, its rhythm dependent on motion and gravity. The universe beyond our horizon may share our laws, but its local conditions may shape time differently. In our region of the cosmos, nearly 14 billion years have passed since the Big Bang. But what does this mean beyond the horizon? If inflation stretched space immensely, then some regions may have aged differently, their cosmic clocks ticking at alternate rates. In some models, eternal inflation produces pockets of space-time forever growing, where time stretches on without end. Each bubble universe has its own clock, its own history. Our universe is not only spatially limited, it may be temporally local as well, one timeline among many. Entropy too enters this story. The second law of thermodynamics states that disorder increases with time, giving direction to history, an arrow of time. Within our observable universe, this arrow points from a hot, dense past toward a cooler, more diffuse future. But what of the unobservable? Could there be regions where the arrow points differently, where entropy behaves in unexpected ways? Some speculative theories suggest that beyond our horizon, time itself might unfold in manners alien to our experience, with beginnings and endings unlike our own. These reflections carry us beyond measurement into philosophy, but they are anchored in science. The relativity of time is no fantasy. It has been confirmed by experiment countless times, from the ticking of atomic clocks on airplanes to the delay of signals from satellites. Time is not universal, it is local. And so, when we imagine what lies beyond the horizon, we must also imagine time itself unfolding differently, shaped by conditions we cannot see. The horizon is thus not only a boundary of space, but of time. We are limited not only in how far we can look, but in how far into the past and future we can know. The cosmos beyond may be older or younger, faster or slower, depending on its history. Our timeline is not the timeline, it is one thread in a vast fabric, each thread carrying its own rhythm. In contemplating this, we realize that the question of what lies beyond is not only about location, but about kind. It is not only where, but when, not only space, but time. The universe beyond the horizon may be familiar in structure yet alien in history, a realm where time itself carries a different story. And so, to press further, we must let go of the notion that time is singular and embrace the possibility that reality is a chorus of timelines, harmonizing and diverging beyond our sight. Time is often thought of as universal, the same everywhere, a single river flowing from past to future. But relativity tells us that this is an illusion. Time is local, elastic, bound to motion and gravity. Astronauts moving at high speed age more slowly than those at rest. Clocks in orbit tick differently from clocks on Earth's surface. The flow of time is not fixed, but relative, and this truth reshapes how we imagine the universe beyond our horizon. If distant regions experience different rates of expansion, their cosmic clocks may not match ours. Some parts of the universe may be older, others younger, depending on how inflation unfolded. Eternal inflation paints an even stranger picture, with new pockets of space constantly budding off, each carrying its own beginning of time. In such a scenario, there is no single universal age of the cosmos. Instead, there is a patchwork of timelines, each one local to its own bubble of reality. We live in one of these patches, measuring our universe as roughly 14 billion years old. But elsewhere, other universes may be newly born or impossibly ancient. Entropy provides another lens. In our cosmos, the arrow of time is defined by the increase of disorder, from the smooth, uniform plasma of the early universe to the complex but chaotic structures of today. This arrow points firmly forward, from past to future. But some theorists ask, could there be regions beyond our horizon where entropy plays differently, where the arrow points in another direction? Perhaps time flows forward in our universe, but backward in another, each universe carrying its own orientation of history. These are bold ideas, but they remind us that the arrow of time is not an absolute given. It emerges from initial conditions, and beyond our horizon, conditions may differ. When we speak of time beyond the horizon, we also confront the ultimate horizon, the heat, death of the universe. In trillions upon trillions of years, stars will fade, galaxies will dissolve, black holes will evaporate, entropy will reach its maximum, and time, as measured by change, will lose its meaning. Yet, if the multiverse exists, some regions will always be young, newly born from inflation. Time itself becomes relative, not only to location, but to the greater structure of reality. Our future heat death may be balanced by endless new beginnings elsewhere. This vision of many timelines challenges our deepest assumptions. We are used to thinking of time as shared, a single measure for all things, but the cosmos suggests otherwise. Beyond the horizon, there may be other flows of time, other arrows, other beginnings and ends. Ours is one among many, a local rhythm in a cosmic symphony. The thought is humbling, but it is also liberating. If time is not singular, then reality is larger than we can ever imagine. The horizon is not just a boundary of space, but of history. Beyond it, the universe tells stories we will never hear, unfolding in tempos we cannot measure. The mystery of time is as vast as the mystery of space, and both remind us that our experience is a fragment of something far greater. The next step is to ask what this means for meaning itself. If space stretches beyond sight and time beyond comprehension, where do we place ourselves within such immensity? To answer, we must turn not only to physics, but to philosophy, drawing upon the long human tradition of confronting horizons with imagination and wonder. The flow of time across the cosmos is a tapestry woven from relativity, expansion, and entropy. Within our horizon, we measure the age of the universe as nearly 14 billion years, but this number is not absolute. It is a local truth, valid for our bubble of space-time. Beyond the horizon, the age of other regions may differ, their histories unfolding along paths we cannot see. In this sense, the universe is not a single clock, but a collection of clocks, each ticking to the rhythm of its own conditions. This realization is unsettling because it loosens one of our deepest anchors. Time is the backdrop against which all events unfold, the stage upon which life, history, and thought take place. To learn that it is relative, local, and perhaps variable across the cosmos is to discover that even time is not universal. Just as space is larger than we can see, so too is time richer than we can measure. We are witnesses to one chapter, but there may be countless others, written in moments beyond our reach. The concept of eternal inflation intensifies this vision. If inflation never fully ends, then new universes are continually born, each with its own timeline. Some may be mere instants old, others may persist for unimaginable spans. The totality of reality would then contain an infinite variety of times, with no single measure to bind them. Our sense of living in the middle of cosmic history would dissolve, for there is no middle in eternity. Entropy also points to a broader truth. The arrow of time, so central to our experience, may itself be a local feature. It arises from the low entropy state of the early universe, a condition that gave direction to change. Beyond our horizon, different conditions may exist. Some regions may host arrows that point differently, or not at all. The universality of forward-moving time, which feels so obvious, may be an illusion born of our perspective. And what of meaning in such a landscape? If time is fragmented across the multiverse, if different universes carry different histories, does our timeline lose significance? Perhaps the opposite is true. Our moment becomes more precious, not less, because it is unique. The fact that we experience this flow, here and now, is not diminished by the possibility of others. Instead, it situates us within a larger whole, a chorus of timelines, each adding its voice to the harmony of existence. The horizon, then, is not only a barrier of space, but a veil over other times. Beyond it may lie older universes, younger ones, or timelines that defy our comprehension. We will never cross into them, never synchronize our clocks with theirs. Yet by imagining them, by acknowledging the relativity of time, we deepen our sense of the mystery. The universe is not a simple line stretching from past to future. It is a web of histories, unfolding across realms beyond sight. From here, our journey must widen further still. Space and time, vast and mysterious, are not only scientific questions, but human ones. For millennia, humanity has looked beyond its horizons, first across seas, then across stars, and now across the very limits of the cosmos. To confront what lies beyond space and time is to enter the realm of philosophy, of meaning, of reflection. The next chapter will explore this dimension, asking what the infinite beyond signifies for us, the observers caught within one small corner of it. For as long as humans have walked under the stars, we have asked what lies beyond. Ancient myths spoke of oceans encircling the known lands, of dragons at the edge of maps, of heavens layered above the world. Each culture framed the cosmos in stories that reflected both fear and wonder. For beyond the horizon lay the unknown, and the unknown demanded explanation. In this sense, our modern idea of the observable universe continues a tradition as old as thought itself. We too live within boundaries, and we too dream of what lies beyond them. The difference is that our boundaries are cosmic. The horizon we face is not the curve of the earth or the edge of the sea, but the limit set by light itself. Beyond it lies not monsters or mythic seas, but galaxies and perhaps other universes. Yet the human response is the same. We weave stories, guided now by physics rather than folklore, but still driven by imagination. The observable universe is our new map, and beyond it stretches the same mystery that called to sailors and poets. Philosophically, the idea of horizons reshapes how we think about knowledge. Science has always promised expansion, the pushing back of limits. Each discovery reveals more of the unknown, but here we encounter a limit that cannot be crossed. The cosmic horizon is not a barrier we can overcome with better ships or sharper instruments. It is a fundamental limit, imposed by the laws of physics themselves. Beyond it, we cannot see, and never will. What does it mean to live with such a horizon? Does it diminish science, or deepen it? One answer is humility. The unobservable universe reminds us that our knowledge is partial, that what we see is not the whole. This is not a failure, but a truth. To recognize limits is to respect the cosmos as it is, not as we wish it to be. Another answer is wonder. The very fact that reality extends beyond sight enlarges our imagination. We can never observe those realms, but we can conceive them, infer them, imagine their possibilities. In this way, the horizon does not end science, it fuels it, giving rise to theories like inflation and the multiverse. For human meaning, the horizon offers both comfort and unease. Comfort because it shows that the cosmos is richer than we can know, that there is always more beyond the edge. Unease because it denies us completeness, leaving us always in the middle of a larger story. Yet perhaps this has always been our place. The ancients stood on shores they could not cross, under skies they could not measure. We stand at a cosmic horizon, no different in spirit, only larger in scale. To see ourselves within this context is to realize that the limits of knowledge are also the sources of meaning. We ask what lies beyond not only to extend science, but to remind ourselves of our place in the cosmos. We are finite beings in an infinite or unbounded reality, mortal lives within timeless spans, small minds within vast mysteries. And yet, by asking, by imagining, by seeking, we become part of that larger whole. The horizon is both barrier and invitation. a reminder that wonder begins where certainty ends. The philosophical implications of the horizon deepen when we reflect on the history of human thought. Every time we have drawn a boundary around our world, we have eventually discovered that reality extends beyond it. Once, the horizon was the edge of the village. Then it was the borders of kingdoms, the curve of the earth, the edge of the solar system, the boundary of the Milky Way. Each time we thought we had reached the whole, we found only another part. The observable universe is the latest and largest of these boundaries, but perhaps it too is temporary. Not in the sense that we will see beyond it, but in the sense that we will learn to imagine beyond it. The horizon also touches the ancient question of centrality. For centuries, humans believed Earth to be the center of all things. Astronomy displaced us first to a planet circling the sun, then to a star among billions, then to a galaxy among billions more. The observable universe seems at first to restore a sense of centrality, for we always appear at the center of our cosmic sphere. Yet this is an illusion born of perspective. Every observer, wherever they are, sees themselves at the center of their own horizon. The universe has no favored point, no privileged location. This recognition is humbling, but it is also liberating. It frees us from illusions of importance while connecting us to the shared experience of all observers, wherever they may be. In this way, the horizon becomes a metaphor for knowledge itself. Each of us lives within a sphere of understanding, bounded by what we can see and know. Beyond that sphere lies the unknown, invisible, but real. Science pushes against the boundary, expanding the sphere, but never abolishing the horizon. There will always be more beyond, always questions unanswered. This does not diminish knowledge, it gives it endless scope. A universe without horizon would leave no mystery. A universe with horizons calls us to wonder forever. Philosophy also asks whether science can ever truly answer what lies beyond. The methods of observation and experiment are limited to the observable. Theories like the multiverse stretch beyond, but they may never be confirmed directly. Some argue that such ideas belong more to philosophy than to science. Others argue that science has always inferred the unseen from the seen, and that the boundary between science and philosophy is not fixed, but shifting. Wherever one draws the line, the fact remains: the horizon forces us to confront the limits of method as well as imagination. For humanity, this confrontation is not defeat. It is a chance to reflect on what it means to seek meaning in a reality larger than ourselves. The horizon tells us that the universe is not designed for our understanding, but it also tells us that our curiosity is boundless. We reach to the edge not because we will ever cross it, but because reaching is what it means to be human. The search itself is our answer, the act of asking our significance in a cosmos that may be infinite or finite, but unbounded. Thus, the horizon becomes not just a feature of cosmology, but a symbol of human existence. We live always within limits, yet we are drawn always beyond them. We accept what we cannot see, and in doing so, we affirm the value of wonder. In this way, science and philosophy converge, each pointing us toward the same truth: that the meaning of the cosmos lies not only in what it contains, but in our quest to understand it. The horizon also forces us to wrestle with the question of limits. In science, we often imagine that with enough ingenuity, every problem can be solved, every mystery revealed. But the observable universe sets a boundary that no telescope, no spacecraft, no future technology can ever cross. It is a wall built not of ignorance, but of physics. The speed of light, the expansion of space, the finite age of the cosmos. These laws combine to create an unbreakable limit. To some, this feels like a defeat. To others, it is a profound reminder that reality is not obliged to fit within our reach. The fact that there will always be more beyond invites us to reconsider the meaning of knowledge itself. If science cannot answer every question, does that diminish its power? Or does it enrich it by placing it within the wider context of mystery? Perhaps the value of knowledge lies not in completion, but in expansion, not in exhausting the unknown, but in forever deepening our understanding. The horizon ensures that there will always be questions left to ask, always new realms to imagine, always wonder to sustain us. In this sense, the unobservable universe is as much a philosophical concept as a scientific one. It embodies the tension between the known and the unknowable, between the measurable and the imaginable. It teaches us that science and philosophy are not rivals but partners, each necessary for grappling with the vastness of existence. Science tells us what we can know. Philosophy teaches us how to live with what we cannot. Together, they form the lens through which humanity contemplates the infinite. This has been true in every era. The ancients imagined seas beyond land. We imagine galaxies beyond light. The difference is scale, not spirit. The drive to know, to chart, to map the uncharted is the same. It is what led sailors into unknown waters, and it is what leads scientists into the deep sky. The edge of knowledge has always been the place where courage and imagination meet. Today, that edge is cosmic, yet the call it gives is familiar. The horizon also challenges us personally. To know that our universe may be one of many, that time may flow differently elsewhere, that infinity may contain copies of ourselves, is to feel both diminished and elevated. Diminished because we are not the center. Elevated because we are participants in something immeasurably grand. Our lives, brief and small, take place within a reality so vast that no word can capture it. To recognize this is to see meaning not as given, but as created, forged by our response to the mystery. And so, the horizon becomes a mirror. It shows us not only the limits of the universe, but the nature of humanity. We are finite creatures with infinite curiosity. We live within boundaries, but dream beyond them. The horizon is not only out there in space, it is within us, the line between what we know and what we can imagine. To face it with wonder rather than despair is to embrace our place in the cosmos, not as masters of it, but as seekers within it. From this reflection, we move at last to the closing vision. If the observable universe is only a horizon, and beyond it lie galaxies, perhaps multiverses, perhaps unknowable realms, then what does it mean to live in such a reality? The final chapter will draw together the threads of science and philosophy, pointing us toward the infinite beyond. The journey through the cosmos brings us always to the same conclusion. What we see is not all that exists. The observable universe, immense as it is only a horizon, a circle of light around us, defined by time, distance, and the expansion of space. Beyond it lies the unobservable universe, galaxies forever hidden. Beyond that may lie other universes, born from eternal inflation or from the branching of quantum possibilities. And beyond even those may lie realms we cannot yet conceive, realities stranger than imagination. To contemplate this infinite beyond is to confront both science and mystery. Science tells us that the cosmos is larger than our sight, that horizons are real, that expansion is relentless. It gives us the tools to measure, to infer, to imagine. Mystery tells us that beyond the horizon there may be no end, that reality may be infinite, unbounded, inexhaustible. Together, science and mystery form a picture of the cosmos that is both rigorous and awe-inspiring. The infinite beyond is not merely a place, it is a concept, a recognition that reality itself may never be fully knowable. We live in a universe where limits are written into the fabric of space and time. The speed of light, the age of the cosmos, the nature of inflation, all conspire to hide most of reality from us. And yet, this does not diminish what we can know. It expands it, reminding us that knowledge is always partial, that every discovery opens more questions. The horizon is not a wall, but a gateway to wonder. Consider the scale of what we already know. Within our observable universe are hundreds of billions of galaxies, each with billions of stars, each star perhaps with planets, some perhaps with life. This richness alone is staggering. Yet if the universe is infinite, then galaxies continue without end, stars burn without number, and life may arise countless times. If the universe is finite but unbounded, then it is still larger than we can ever measure, wrapping back upon itself in ways we cannot imagine. Either way, the beyond is vast, and our place within it is both small and meaningful. For smallness does not erase meaning. To be part of an infinite cosmos is to share in its grandeur. Our lives, brief as they are woven into the same fabric that stretches across light years and eons. The atoms of our bodies were forged in ancient stars. The thoughts of our minds arise from matter shaped by cosmic history. We are not outside the universe looking in. We are the universe, conscious of itself, asking what lies beyond. The infinite beyond is thus not only a scientific vision, but a human one. It challenges us to see ourselves not as masters of the cosmos, but as participants in it. It asks us to embrace humility and wonder, to accept that we may never know the whole, but that knowing part is enough. It calls us to live not as if the horizon is an end, but as if it is an invitation. For every horizon reminds us that beyond what we see, there is more. The infinite beyond is an idea that reshapes not only cosmology, but the way we think about existence itself. If the universe is infinite, then every possibility is realized somewhere. There are galaxies just like our Milky Way, planets just like Earth, and perhaps beings just like us, separated not by time, but by distance beyond imagination. In such a cosmos, repetition is inevitable, not because the universe seeks to copy itself, but because infinity ensures that every arrangement of atoms must occur. This vision is unsettling, for it dissolves the uniqueness of our world. Yet it is also inspiring, for it shows that existence is richer than any single version. If the universe is finite but unbounded, then the meaning is different, but no less profound. In such a cosmos, there may be no endless repetition, no infinite copies. Instead, there is wholeness. The universe is vast, but self-contained, complete without edge or outside. In this view, to ask what lies beyond is to misunderstand the question, for there is no beyond. The cosmos is all there is, complete in itself, and our role within it is not diminished by its boundaries, but defined by them. The multiverse extends both visions still further. If eternal inflation is correct, then infinite space may be accompanied by infinite universes, each with its own laws of physics, its own timelines, its own versions of reality. If the many worlds interpretation of quantum mechanics is correct, then every choice and every event branches into new universes, multiplying existence beyond comprehension. If string theory's landscape is real, then the cosmos may contain universes with entirely different constants, some lifeless, some rich with galaxies, some perhaps hospitable to life beyond ours. Each of these pictures pushes us further from certainty and closer to humility. We cannot say which, if any, is true. We cannot travel to the beyond, cannot test it directly. Yet the theories that suggest it arise naturally from physics as we know it. They are not fantasies invented to fill gaps, but logical consequences of models that already explain much of what we see. The infinite beyond may be speculative, but it is speculation grounded in science. Philosophically, this challenges our sense of meaning. If there are infinite Earths, are we diminished? If there are countless universes, is ours unimportant? Perhaps not. Perhaps the truth is that meaning does not depend on uniqueness. A sunset is not less beautiful because countless others exist. A life is not less precious because others live too. Meaning arises not from rarity, but from participation. We are part of the cosmos, part of the infinite beyond, and that connection is enough to give significance to our existence. The infinite beyond also calls us to a new perspective on knowledge. We may never know the whole. The horizon will always hide more than it reveals. But the value of science is not in final answers. It is in the expansion of understanding, in the widening of perspective, in the act of reaching. To know that there is more beyond is itself a form of knowledge, one that humbles and inspires. The beyond may remain unseen, but it shapes the way we see ourselves. And so we stand at the end of this journey, gazing into the infinite beyond. What lies there, we cannot say. Galaxies without number, universes without end, possibilities beyond imagination. The horizon keeps its secrets, but it also gives us wonder. The infinite beyond is not a destination, but a call, a reminder that reality is larger than us, and that our task is not to master it, but to marvel at it. The infinite beyond is not meant to give us answers, but to remind us of questions. Our science shows us the boundaries of what can be known, and those boundaries themselves point to greater realities. We live in a universe filled with light, stars, and galaxies, but these are only the visible surface of a deeper ocean. Beyond our horizon, there may be unending space, or there may be closure without edges. Beyond our universe, there may be others, each carrying its own history of time. And beyond even these, there may be mysteries our physics has not yet imagined. What matters most is not whether we will ever see them, but that they exist to be thought about. To ask what lies beyond is to accept that we are finite beings gazing into the infinite. It is to embrace wonder as a way of living with the unknown. The stars above us are not only suns in distant galaxies. They are symbols of a reality that exceeds all boundaries, reminders that our horizon is not the end, but the beginning of imagination. And so, the journey comes full circle. We began with the cosmic horizon, the limit of what we can see. We followed the expansion of space, the inflation of the early universe, the idea of multiverses, the search for clues, the geometry of space, the relativity of time, and the reflections of philosophy. At the end, we return to the simple truth. The horizon is not a wall, but a call. It invites us to wonder, to imagine, to reach with thought where light cannot go. Perhaps the universe is infinite, galaxies repeating forever. Perhaps it is finite but unbounded, a grand whole without edges. Perhaps there are countless universes, each with its own story. Whatever the case, the infinite beyond is real, and it will always remain beyond our reach. But that is not cause for despair. It is the source of awe. To live in such a cosmos is to live in mystery, and to live in mystery is to live in wonder. We may never know what lies beyond the horizon, but we can always ask. And in asking, we become part of the story. We are not only observers of the universe, but participants in its endless unfolding. The horizon is where knowledge ends, but it is also where meaning begins. Beyond it lies the infinite, and beyond the infinite lies wonder without end.